What's up, what's up? Welcome back. Today we're working on my x86 operating system, currently titled Stream OS, because it's an operating system that I'm developing on Stream. Fun names are welcome if you have good puns. I need to hear them. So eventually this will have to be renamed. In its current state, we have this like operating system. Operating system is kind of like a strong wording for what this is. We have like a kernel, and it boots in a virtual machine, QEMU. Let's see if I can if I run this with release mode because it's too slow in debug. We get like a virtual machine. It pops up. It boots. We have like graphics. We have like user input. Right, I can like play this game. While that's going, there's like logs that are being written to the serial console. And when you're written to the serial console through QEMU, we can like forward that to standard in and out, so we can get like nice little. It like behaves like a normal application from our perspective, but really it's doing OS stuff. We have like an Ethernet stack, so if I try to like netcat to this, which is just like, hey, open a TCP socket, and I'm gonna like drop some shit in there. I can say like hello, and it says like, oh, I found hello, and it even writes it back to us. So we have like our Ethernet card working, which is over PCI, which has like we need to do like address resolution and TCP and all that jazz. We have like memory allocation, but we're doing like no paging, so we have like just a contiguous chunk of memory that we like allocate chunk sections from, which gives us like stuff like Rust's like vectors and maps and stuff, and we have like access to system clock. So we've got like kind of like the pieces for an operating system, but we're not really doing anything useful right now. What we're working on currently is trying to get like multi-core support working. So over the past few streams, we've kind of been like preparing the code base to be used for multiple threads by making everything like mutex protected or using atomics, lock-free queues, etc. And then we've recently managed to like boot the second CPU. And we've like kind of like proven in our debugger that we are in Rust code in our second CPU. But at the end of last stream, we were kind of stuck in this state where our stack on the second CPU was just like totally fucking busted. And I did solve that off stream. So I think probably what we're going to do today is I'm just going to like recap that fix and then like try to get going on we can like run a function, sure, but like if we want to do something useful with that function, we need some way of like communicating between like the bootstrap processor and the secondary ones. And so probably what I'm going to do is I'm going to try to like find some sort of way to pipe arbitrary functions from one CPU to the other, and then we can just say like, hey, CPU2, run this shit, go, and then we can do whatever we want. Yes, that's what we want to do today. So at the end of last stream, we were kind of in this state where, how do I prove this? If I run in GDB, where running in GDB means we boot the virtual machine, QEMU, the virtual machine, he keeps track of like his instruction pointer and all of his memory and all of his registers. And then I can say like, hey, GDB, can you like talk to QEMU and maybe like put a breakpoint in this spot? And when QEMU sees that breakpoint, he goes like, oh shit, stop, instead of executing the next instruction. Great for us. So if I like look at this, I set a breakpoint at where do I want to show this? Maybe here. So in our bootstrapping for the secondary CPUs, we have like this like chunk of assembly that we went over a couple streams ago. But like the core of it is like I'm boot in 16-bit mode. I set up this like table that sets permissions called like the global descriptor table. I like set myself up to be in 32-bit mode, and then I execute this like jump that references this table to put us in 32-bit mode. And then all we do here is we try to like set up a stack and call our like Rust function. And if I go to our Rust function, which I think is, oopsies, I think is over in main somewhere. All we're trying to do is like do like a little debug log, or an info log, I should say, that says CPU ID booted. So this stuff is where we were getting stuck last stream, was that we were trying to push a value to the stack that like flags, hey, I am CPU1. And we were trying to figure out why when we pushed CPU1 to the stack, we weren't seeing it on the stack at all. So here, I think in my debugger, if I disassemble, kind of like where we are in code, I think it's 0x810000, I should see like here, we're like, for some pushes. And so if I say like info registers, oops, I just flung through a bunch of windows. If I say info registers, I should see that like EBX is 1. So all of these instructions say push EBX should like push 1 to the stack. And if I look at my like stack pointer, I have it set right now to this value, 2OB000. And if I like jump over an instruction and I info registers again, we see the stack pointer move. Great. And if we disassemble again, we've like moved, we should have pushed something to the stack. And what we were finding was if we like dump that section of the stack, so if I say like print 10 bytes from the current stack pointer, we see a bunch of zeros. And that's like fucking broken. One of these things should be a 1 because we just put a 1 on there. And my guess at the end of last stream that I didn't have time to validate was that the global descriptor table was not really in a good state because we just kind of like took this chunk of code from symmetric multiprocessing in it, and in here is where they like we just copy pasted their global descriptor table, and I just like assumed it was sane, but I didn't actually check it in any way. So all I did was I just went into my version. We have this like GDT init stuff in Rust, which was a whole shit show to get going. But we can kind of just say like, okay, we've constructed this like GDT and let's just print out what it looks like. So I did for entry in entries, where these are like the entries in our table. This is just a GDT segment, which we called it in Rust, which here is a U64. So I can just say print line entry. I think I have to print it in 2 sections. If I look at like this implementation, it's like a 64. The values in this table, they're these like complex things that say like 64 bits, where like some of them are talking about like the range of the memory that you're talking about. Some of them are like access permissions, and then like these like base like pointers are like split up over multiple sections because you have like 16-bit and 32-bit versions of this table that have to like both work together. Anyways, so it's kind of complex, but the core of it is 64-bit value, and we're punching 32-bit values into our assembly file. So here, if I just print this as, I can say .long, and then print the lower half and then the upper half the value. So here I can say entry .0 and 0x1, 2, 3, 4, and then here I can say entry .0 shifted right by 32 bits or something. I think if I do that, or go run, boot the OS, I can just copy paste this. Let's paste it in hex so that it's like a little bit, I don't know, it's more sane to read. When you're working with like bitmask stuff, it makes more sense this way. So we can just copy paste this into our assembly file. And where do I look here? I think that this is in boot.s. So here I can just replace these things that they put in with this. And so here's what we have now, and this is what they had before. And so you can tell that they're different in some way. I don't really know what the differences mean or are or whatever, but they are different. So let's just load our version. And I'm pretty sure when I did this, everything just started working. So we'll do the same test where we start at GDB. GDB equals 1, cargo run, boots a thing like this. And now if I restart this debugger, one sec, restart it, boom. So now we're at that same spot where if I disassemble, we're about to push some shit onto the stack. And now if I say info registers, we should still see EBX is 1, which is what we're trying to push to the stack. And so now if I like jump a couple instructions, and I do the same thing where I say like print out like 10 bytes from the stack pointer. Now we're starting to see some ones in there, which we didn't see before. So it really was just some sort of like permissions issue. And that like fixes a whole bunch of stuff, right? Because before, like our stack was broken, so we would have like local variables, and they just like weren't getting set, and so we'd just be like doing like null derefs everywhere. Every number that we expected to see anywhere was just 0, and that was just like fucked. So, pretty easy fix. Should have seen it coming. Probably should have just done it at the end of last stream, but it is what it is. And so now we're kind of in a spot where we can just run arbitrary code on the secondary CPUs. So, like if I go into here and I go into our AP startup stuff, here I'm doing like an info log that says CPU ID booted. I can like maybe do like a print line as well. I can exit the OS after with exit code 33. So I think that if I do this, we should see a couple things printed, followed by we see an exit. CPU one printed. We do see 148 here, which is not the exit code I expected to see. Does that matter if I do like 25? That worked. So that's kind of interesting, where some values are broken and some values are not. Oh no. I think I probably just I probably misclicked something. I was reading the wrong number. If I type 148, 148 comes after a stop or a something. Anyways, doesn't matter. Point is, we're running code. Our stack's working. We're getting what we want to see. And so now we're kind of in a spot where we can start trying to do something interesting. I'm sure we'll probably come across more bugs. But yeah, that's what we want to, where we want to go. So probably the thing to do next is find a way to communicate between CPU 1 and CPU 2. And so I think where I want to go with this eventually is it'd be kind of funny to like runtime generate the trampoline and inject a pointer to like avoid, you could like pass in to this startup function. You could just pass in like kernel is like a const pointer to or like a const kernel pointer or something, and that'd be kind of fun to like runtime generate the machine code to like stick this exact address on the stack when we boot, and then with this kernel, it doesn't have to be like in static memory or anything, it can just be like a normal allocated pointer, blah blah blah. But for now, what I think I want to do is the simpler thing is to just use what's it called? Just like a static variable somewhere. And when we boot up our secondary CPUs, probably we like register ourselves with this like static area of memory. And then we could have some sort of API that says like, I'm going to like send a function over to that CPU to run. And then on our side, we're just like pulling that, we're just like looking for that function. And if we see it, we run it. So let's try to look at that. So we'll say what, like inter-processor communication of some sort is what we want to do next. Yeah, okay. So let me just make sure that we're like in a good state. That's no actual changes. We just kind of, yeah, nothing in here is worth saying. The second half is worth saving, so. Uh-oh. Did I crash? No, are we back? Camera's working right? Okay, I don't know what the fuck that was. So this stuff's not worth keeping, but this is worth keeping. And this is not worth keeping. Okay, so we just nuke our changes and do like a quick cargo run, release, just to make sure that everything's still working the way we expect. Give it a sec. Yep, so we're booting. We see CPU 1 booted in our logs. Great, everyone's happy. Okay. So probably, it's probably time to start trying to move this like multi-CPU stuff into like a sane spot. So this multi-CPU stuff, one of the way it works is, we parse these like ACPI tables. These ACPI tables have like pointers to other tables. This table has like a list of programmable interrupt controller stuff. And the way it works is we have like CPU 0, well, maybe any CPU, but really CPU 0, but like maybe any CPU, that they call the bootstrap processor. And this is set by the BIOS or UEFI or something. Like before we even get to like our operating system, we've determined which CPU is going to run. He's got this like advanced programmable interrupt controller on him. And then we have these other CPUs that are called application processors, but they're the same thing. Like there's no special thing about the bootstrap processor. And they also have APICs. And these guys are connected through a bus. And so the idea is, this guy says, yo, CPU 2 or APIC 2, could you like boot your CPU? Here's like an address to jump to. And then this guy does it, and that's it, right? And so the reason that we have to parse these ACPI tables is to get this like descriptor to like a point that has a pointer to the where is it? Pointer to like the APIC that we want, like our APIC. We also get like a list of other APICs with APIC IDs, so we can see like, oh, we have 4 cores, or we have 2 cores, or we have 9 cores. And so what we do is we need this address, because this is like a memory mapped device where you can like write specific registers to like trigger this like command to send. And you need this stuff to trigger, to like know who to talk to. Great. So we have this like module in our Rust code, ECPI, and this is like supposed to be parsing of all the tables. But what ended up happening as we were like trying to poke and prod is we ended up just like also just when we were iterating over these tables, just like booting the other CPUs as part of that parsing, and that's wrong. And so we should probably, it's probably time to start pulling out this like booting stuff into like another module that has like his own localized like static variables for interprocessor communication and stuff. And so the things we need to pull out are, we need to pull out this our APIC address as well as the processor list that we want to boot, which I think matches up here. The things that we pass in here are the ID of the processor to boot and the local APIC address, as well as like a reference to time, because we need to use like some sort of like, oh, wait 10 milliseconds before you do this, to make sure they have time to boot and shit. So it's probably time to pull that out. So probably what I want to do is make like a multi-processing mod. Sure. Multi-processing. Maybe that's, fuck it, we'll figure it out later. Maybe I'll leave it forever. Who knows? So here we need to use that module. And here we want to pull out like the booting stuff over there probably. So here we have like our CPI stuff. We have this boot APIC, and this should just go over there. This stuff also goes over there. Okay. We need to fix some imports, so we just pull these in. And I guess probably getting CPU ID is also a like multi-processing concept, so we'll just shove this in here too. We write this file, we add it to Git so we don't forget later. We run our little linters, and he goes like, what the fuck, I can't find these functions. So for now we go into the ACPI and we just say what, create multi-processing boot APIC. And there was somewhere else where I had CPU ID, and this is in our crate multi-processing CPU ID. So this should compile. Beep, boop, beep, boop. Great. We still see CPU1 booted from the CPU, and we see like our game running, so everything's kind of like still kind of working to some extent. Okay. So in reality, or like if I were to be a good developer with an eye on the future in any way, shape, or form. So right now we're like booting in this like print entries function. Really, this should turn into a iterator, like something that like exposes the entries. So in this like multiple APIC descriptor table, we have like things that come out like, oh, here are the other APICs, and here's our APIC, and like here's some other shit about them, and here's like the mucks for them, and we should really like maybe expose all of that to the external user. So someone else should like get a handle to this table, and he would say like, hey, I'm gonna iterate over these entries, and like I'll keep track. I'll like write down when I see APIC IDs, and I'll write down when I see the like pointer to my local APIC and stuff. And then I'll use those to boot the processors. But I don't really want to do that right now. I don't think I have to do that right now. I think I can kind of like get away without it. So for now, I'm just going to leave this like print entries function as like the function that will boot the secondary processors. Maybe I'll like rename this to like, that seems fair. I'll rename this to like, I don't know, iterate, entries, and boot or something. And I'll just acknowledge that this doesn't belong here. So I'll just say fix me, move booting to another module. In here, I'll say fix me, move code juggling to another file. This is like some like fucked memory copy where we take some assembly that's like been assembled and placed in like a higher like normal code area, and we copy paste it to like this like really fucking low address that we don't even like check if anything's there. I don't know if I'm just like clobbering something important, but we fuck it. Plays it, whatever. This shouldn't be used because I think that our kernel starts at address like 1 meg or something, and this is like way below this. I think this was used during like BIOS time and boot loader time, and so we're just like clobbering something there, but that's fine. It doesn't really matter. So you know, we should probably protect this, do some like more sane checks by like it looking at our memory regions and seeing where it's safe. But whatever. What we're doing here is we're copying our code for the trampoline to get us into like normal Rust code. Into this really low address, because the API for booting, he like assumes that how do I say this? He can only put very low addresses for where to jump to for the new CPUs. He can only like write down really low addresses. Let's see if I can find that documentation somewhere. It would be in like the APIC stuff probably. Interrupt command register, probably here. Somewhere I say like, hey, start up, and vector number for starting page number. Yeah, so I have bits 0 to 7, so 1 byte. And I can say, here is the starting page number for where you're going to jump to. So that only gives me like, what, 0 to FF? That sounds right. 7 bits? Yeah, 0 to F. So that gives me like 255 pages I could jump to, which is like really low. Yeah, so that's, well, actually, is that true? What's like, so I've written like 8 here. If I wrote like FF, yeah, that's still not very much memory. Presumably because that's like 16-bit mode as well. Anyways, so we copied this stuff over here, and this shouldn't be here, but that's fine. It's fine. Okay, so what are we gonna do? When we boot the processor, we're going to jump into like our processor init, which right now lives in main. Let me just make sure that everything's compiling still. I fucked up this when I renamed this from print entries to whatever the fuck I just named it to. I didn't rename it everywhere. Print entries. Oh, I just didn't save the file. Oops. Okay, everything compiles. We're moving. And let's move this like AP startup stuff. This can just go into the multiprocessor area as well. Okay, cool. So if I cargo run, everything should still be happy. I didn't save something. There we go. All right, everyone's happy. We still have our CPU and booting. Great. So what do we want to do here? Here we're gonna want to like inject our CPU ID into some form of like static memory, probably. So somewhere we're gonna have static. What are we gonna put here? I guess the simplest thing to do is just like queue up CPU IDs with like channels to talk back to. So like for each CPU, maybe we'll define the like user or like the kernel side interface first, the bootstrapper processor side interface first, and we can kind of see what we want to do from there. It'll probably like evolve nicely. So let's call this what, like CPU manager. That's lame. I don't like that as a name. Like CPU list, CPU communicator. Manager's fine. We'll come back. Well, it doesn't really manage the CPUs. All he's going to do is like send functions to him. So maybe dispatcher is more CPU function dispatcher. Whatever. That's good enough for now. And what's he going to do? He's going to say, he's going to have some APIs on him. And one of them is going to be like execute, who's going to take in some form of function. And maybe even a mutable function. Or a one-time call function. That seems more reasonable. He's going to say, like, call this function, call it once, and then you're done. And he's going to take in himself, by reference, probably. And the function. And what's he going to do? He's going to want to, like, have a list internally of, like, CPUs. And what's he going to want to do with them? He's going to want some way to like send the function to them. So let's just say that we had like a vector of CPUs. We could maybe assume that the CPU IDs are linear and they'll all be valid. But like say that there's like something wrong with CPU 3 and it doesn't boot right and we have like 4 CPUs. Maybe here we have like a hash map, which is like kind of stupid, but it just means that I don't have to think about like indexing correctly. And so we'll go from like processor ID to what? Like some way to send the data. So like we'll have like a double-ended queue where we can just push the function. The functions will each have like unique types that we push. So we're going to have to like stick those behind some sort of like indirection. So we'll use like a pointer type to put them on the heap so that they have like dynamic resolution of functions and shit. What do you call that? Why am I blanking? I can't remember what it's called. vtable? No. Wow, I'm blanking. Runtime type deduction, whatever. Okay, and this will have to be like mutex locked, presumably. Right, because we are reading to it from one end and writing to it from another. And now we have like a bunch of things that we need to import. So we'll use hash brown hash map. We will use, from my crate, we need to import my mutex. So it's util, async mutex probably. Async mutex is going to be a problem, so we'll use a spin lock instead. which means that this needs to be a spin lock, right? We need to use alloc box, which is the like Rust's unique pointer type, and then we also need his double-ended Q implementation. So I think it's Q, what, vec collections. Here we go, vec dq. Okay, did we get everything? He doesn't like this like function once because he needs like this. And now he's bitching that there's a very complex type, but you can shove it. I will do what I want, Clippy. I guess I can do allow Clippy type complexity. Fuck you. Okay. So this is pretty reasonable. So what's he gonna do? When he gets over here, he's just gonna say, he's gonna find us. He wants to like find which CPU isn't doing anything, or he just picks one, or we pick one from externally. Yeah, fuck it. We'll just say CPU ID is a U32, and maybe the CPU ID comes first because if we were to inline the function in the function call, it would like look prettier this way because then we could do like CPU dispatcher.execute on 1 and then like pass in our function like this. That's like nicer than having to stick the 1 at the end. Okay, so he's gonna say maybe he's gonna be able to fail. His success, he's gonna do nothing. He's gonna say nothing. But on failure, he's gonna say what, like CPU like execution failure or error maybe. And we're gonna have like, I'll just say that maybe this is the only thing that can go wrong right now. Later we'll figure out types if we need more types of errors to flag back, but right now we'll just say it didn't work. So we're gonna say, we're gonna look at our CPUs, and we're going to try to get the CPU with the CPU ID passed in. And if that's not okay, if we didn't find it, that's an execute error. So we'll say let Q is this. Then what we're gonna like Q dot lock, right? So we're gonna say let Q is equal to Q dot lock because this is a spin locked thing, and then this is a mutable thing after we lock the mutex. And we're saying like what, Q push back F after we box it. Type F might not live long enough, so we'd have to say that this has static lifetime. And now it works. Because otherwise Rust will be like, oh no, you're not allowed to store this forever. Oh no. I'm Rust and I worry about things like that. It's like, yeah, I get it. Thank you. God. Shut up though. Okay, and that's all we're gonna do on like execution side. So then we can say like, well, what are we gonna do on the reader side? Well, somehow we need to like get this information here. So maybe what we do is we have like a service function. Depending on where I want this to live. I think this makes sense. And what he's going to do is he's going to just watch for CPUs to boot. So maybe what we do is on every CPU boot, we write to some sort of like static queue. So we'll say what, like boot info queue. And he's going to be something that can live in static memory. So this gets kind of complex because I don't remember which types I'm allowed to construct in like static memory because they need to be like constant constructible so they can just like copy paste the memory and where they want it to go. I think my spin lock should be, so if I just did like spin lock option vec dq something, is this legal? Let's try. So here we'll say spin lock new, none. We'll just see if this is allowed to be constructed. Yes, that's valid. Valid and fair. What if I don't put the option in here? Oh, weirdly, oh. I actually thought that wouldn't work. I'm surprised that vecdq is const constructible. But it is. Okay. So that's actually really easy. Because then all we have to do is on boot, what are we going to put in this queue? It's going to be a CPU ID. As well as a queue to push. So this is going to be, hey, what's up? Welcome. So here we're going to insert, I guess we'll just call it a boot info. Boot info like this. And what does he have? He has his ID, which is a U32, as well as his like queue to work with. So he'll say queue is a spin lock vecdq box dyn function once. Here is a queue of things to run. I also forgot that this needs to be a shared reference to a spin lock, so now I have to throw this behind an arc for even greater type complexity. Let's go, baby. I like seeing 1, 2, 3, 4, 5 angle brackets right next to each other. It starts to look like a fucking merge conflict, you know, when you have like a git merges, they say like head, and then they say or like other, and they have like part A, part B, so like this is like the conflict. So I like when the types start to look like merge conflicts because it's like, oh, it's just so fucked that I can't tell anymore. I don't know. Okay, so we need to pull in this like shared reference shit. So I think it's under like sync arc in the alloc crate, right? And where arc is just like a reference counted atomic shared pointer thing, analogous to shared pointer in C++. And now I'm kind of agreeing with Clippy. This is fucked, right? Let's just let's just agree. So we'll use some type annotation. So we'll say what, like function q is a vec dq box dyn function once, and then we'll have like type shared function q. And he's gonna have like arc spin lock function q, and those are like more reasonable names, and I can just write shared function q. No joke, I was like, I hope someone is streaming OS Dev in Rust. There's no way, right? There's no way that you would just come like think that and then come here and find it. That seems like so unlikely. Okay. Shared function q. Which I misspelled because I missed a caps lock, and we don't need this anymore. Okay, so cool. Then I think all that we have to do is on second processor startup, we like have this boot info queue, and we lock it. We put this in a scope so that our lock doesn't live for too long. And then what we say, queue push back my CPU ID. So we have ID is CPU ID, and the queue is a new thing. So we'll say, fuck, this is the boot info queue. And we'll say, the function queue, I guess what is what, a, oh god damn, arc new spin lock new vec. Can I just do default? Default. Come on, baby. Wow. I guess we don't know what it is yet. So we'll say q is arc clone function q. Cargo check. The trait default is not implemented for spin lock vecdq box. Yeah, I don't know what I was expecting. Sorry, I swear I thought that was so unlucky. That's really funny. That's shocking. Okay, so I guess I do actually have to write like spin lock new what's in here? Function queue new. I think that is probably right, and then we can say arc new spin. Oh, and that's actually not so bad. That's only 3 layers deep. Usage of an arc that is not send or sync. Why? Is my spin lock... Did I not implement send and sync for my spin lock? I did. Why does he think... Oh, it tells me exactly what it doesn't like. Cargo check. Cargo clipping maybe is which one of those it's going to give it at. Send is not implemented for spin lock. Okay, fuck off. Fuck off. That's not helpful. Why is it not implemented for spin lock? Okay, so the trait send is not implemented for spin lock, vectq, blah, blah, blah. Required for arc spin lock to implement send and sync. So if I look at my spin lock implementation, he implements send if the thing underneath implements send, which means that what? Our function queue somehow doesn't implement send? vectq doesn't implement send? Why? Simple send. Let's look at maybe vectq. This guy should implement send, does he not? He implements send. Yeah, so he should be sendable. If the thing inside is sendable, I see. So is my box dyn fn once not sendable? Oh. It is if I write this. God damn. Dude, the Rust type system, I love it for keeping me safe, but I hate it for being a pain in the ass. Okay, so that means that this guy also has to be send plus static. There we go. What the hell is that syntax? Yeah. Yeah. I know. Okay. So now we have our function queue. We've pushed him in. And then we can just, here, we can say our loop is now, instead of going to be just halting the CPU, we're going to do, what? We're going to wait for the queue to be populated. So we're going to say function queue lock, and then we're going to pop. So we'll say let f is equal to functions pop front, right? Because we're going to say we're going to do our function. We're going to look at our functions in order, and then we're going to call our function. So I think we do like f like this. And then here we have to say if let sum f is equal to this. Then we call the function. And then else, for now, we'll just turn off the CPU, but I think that's going to be a problem. Or I guess for now, we'll just, like, fucking hot loop. But we will need some way to, like, halt CPU and wait for something interesting to happen. Like, we need some sort of condition variable style thing. I'm actually concerned about this because I've just straight up disabled interrupts on the other CPUs. But maybe we can flag with like a software interrupt and that'll be fine. Yeah, that should probably work. I hope. We'll see. Okay. So here in our like function dispatcher, we're gonna have to like listen for this queue. Which means that like we're kind of in this like fucked state where if we constructed 2 of these and they were both listening, that would be like a big problem. So probably what we'll do is we'll make a public, these are all public functions, right? These are going to be used externally. He's going to return our like function dispatcher. Sure. And I guess he should be able to fail. So he'll try to return this, or he'll say CPU function dispatcher error. We'll just call it that. Hey, yo, what's up, what's up? Then we'll make an error for this, CPU function dispatcher error. And I guess what we'll do is we'll just make like a static variable that says like dispatcher active is an atomic bool. And he's atomic bool new false. Not much. How about you? Oh, we're just having fun doing some multi-core stuff. So here he is crate. Not from crate. We have to use core. Let's sync atomic bool. And we're almost certainly gonna have to use ordering as well when we actually use it. And so here we'll just say if dispatcher active load with relaxed ordering, I guess. Probably. I think that's fine. We return an error. Otherwise, we store that we're the ones using it. Oh, I guess we have to do like a compare exchange in case two people try to construct these at once. So we say what? Let active is equal to dispatcher active.load. We put this in a loop. Then we try to set it to true. So we say dispatcher active compare and exchange weak. He takes in the current value. He sets it to true. And the order, we'll just use relaxed ordering for both. And this guy, I think, returns an error. Yeah, it's what? If we succeed, we break. So if let okay is equal to this, we break. Great. And here we move this guy here. Then we ensure that we only create one of these guys. Great. And then we can say CPU function dispatcher is, he has CPUs of hash map new. And I have to wrap him in okay because he's a failable thing. So I say this is okay. Okay, there we go. Oh, the linter wants me to write is okay here because that's very slightly more readable. Okay, fine, fuck off. We get it. Okay, so in his service loop, what's he gonna do? He's gonna watch this info queue. And here we're gonna use like async Rust to try to be a little bit more intelligent to avoid like hot looping like we are on the other side. So what we do here is it also avoids like getting stuck in this function. So we need to construct a future. So we'll say, what is this called? This is boot info queue available. And we'll say impl future for boot info queue available. We cannot find the trait future, so we're going to use Rust's future type, which comes from here. I think it's core future. And then we're also going to need a core task context and poll for the implementation. If I remember correctly. Here I say, hey, indexer, or yeah, could you just fill this in for me? Thank you. Oh, we also need pin. Of course we need pin. Okay. So what we're going to say is, let's find a way to poll for if this is available. So what do we have to do when we poll? First, we check if the there's anything in here. So we'll say, let queue is boot info queue dot lock. We're going to spin lock on this to get it. And then we're going to say, I guess the output of this thing, once we've determined that there's something available, we'll just return it directly. So we'll just say, the output of this is a boot info. And we'll say queue.pop front. And if we get something, we return it. So we say, we are ready, poll ready, and here's my value. And if we don't get anything, we say poll pending. Now the problem here is that we need to associate some sort of wake up with this feature. So right, like if we just did this, the first time we run our service function, we would say, oh, there's nothing there. And then we just give up, which is wrong, right? So like what I would do here is I'd say like boot info queue available dot wait. And I'd say what? Let info is this. And what would happen is, on the first call iteration of this loop, it would go, hey, nothing's there. And I'd be like, okay, I'll take a nap. Sleep time. Sleep time for me now. And I would never call this again until someone told me to. And the problem is that like we actually need someone to tell us to, which means that we're actually like fucked. So I think this is actually what we can do is we can set we can just like provide like sit a waker here. So we can say like static waker is an atomic cell, which is like a thing that we've created, which is like an atomic way to swap in a value. We can just put this in static namespace. Namespace is the wrong word because we're not in C++. But whatever. Here in our utility crate, I think that's where we defined it. Or our utility module, it's atomic cell. Great. And we need to pull in the task waker. So this is the way that we tell ourselves it's time to wake up. Oh, it's non-const. Fuck. Really? Can I make this const? Alright. I love it when it's that easy. You just write the word. Okay. So then what happens is here, if before I say I'm pending, I just say waker store our waker. And what that does is it says like, okay, now I know somebody's waiting. Somebody, the only person who could be waiting is waiting. I guess maybe this needs to be a mutable reference. I'll think about that later. But we'll say like, somebody's waiting. And then when we inject some info into this queue, we just say if let sum waker is equal to waker load or get, we wake them up. Nap time is over. And hopefully that means that this feature will work correctly. Hand wavy, I think that will work. And so maybe what we'll do for now is we'll just say, we'll put a little log here. And we'll say found boot info for CPU. And we'll say info.cpu ID, or is it ID? I can't remember what I wrote here. I did just write ID. Okay. Very cool. So I think we have all of like the bones in place to start executing, actually. I think there's like a good chance that this will actually just fucking work, which is kind of cool. So let's go over to main. And maybe what we'll do is we'll like in our kernel, we'll have a reference to like a CPU dispatcher. And he has a CPU function dispatcher. Who needs to be public. So which means that down here we just need to say like CPU dispatcher is equal to CPU function dispatcher new. And here we pass in CPU dispatcher. We need to actually import this. Hey yo, what's up? Welcome. What goes in here? We have somewhere we need to import that thing here, which is from multiprocessing CPU dispatcher. Nice. This guy goes here. Everyone's happy. Mismatch types because we need to say, if this doesn't fucking start, we're just going to crash and say CPU dispatcher instruction failed. And we just need to derive debug for this guy for that to work. All right. All right, man. Cool. So, oh, gifted sub. What a nice guy this guy is. Thank you. Okay. So what are we going to do here? We're going to actually, we have to, when we get this info, inject it into our CPU queue. So we'll say self.cpus insert. We take the ID from the info, and we just inject the queue. So info.queue. Easy. Easy peasy. Which means that this service function has to be mutable, which makes sense. Which means that probably this execute function will never work. Because if I have a mutable reference, so we actually need to like, oh, this needs to be behind a spin lock. Or a mutex, an async mutex. That'll work. That'll work. So here we can pull in our async mutex, great. And here we're going to create a mutex. And then here we just need to lock. So we'll say let CPUs is equal to self.cpus.lock, and we await it. We insert it here, then this guy is not mutable, and then here we say let CPUs equal self.cpus.lock.await. And this has to be an async function as well. All right. Everyone is chilling. Now I think all the pieces are in place. I think. So if I go back over to main, we have our CPU dispatcher, and I think that all we should have to do is we have like a list of things that we're doing, and on the list of things that we're doing, we'll service the CPU dispatcher. And then I think if here I just say let run function on CPU is going to be like an async block that just says self.cpudispatcher.execute, and we'll just pass in a function that says like, we'll print line hello Mick from CPU, and we'll pass in CPU, we'll call like multi-processing CPU ID. And we'll execute this on CPU 1. And then one of the things that we're going to do is run function on CPU. All right. Okay, and I guess we unwrap this for now. So I think that, dude, if this works, I'm going to lose my shit. It's so rare that something works the first time like this, but I just wrote a lot of code and we'll see. So let's just cargo run. God damn, that feels good. Woo! Okay. So, God, that's so fucking sick. That's so sick. Okay, so we actually did, just from our Bootstrap processor, we just wrote a random arbitrary function and sent that over to the CPU 1, and CPU just fucking ran it. And all of the like queues and stuff that we needed to get there all just kind of worked. God damn. Unexpected. Very, very unexpected. So yeah, that's was surprisingly easy. Let's think. What do I want to do next? I kind of assumed that there were going to be bugs in here to sort out. I wonder if there's like a way. what do I want to do? Eventually, so the long-term plan, or the short, maybe medium-term plan, is that now we have this like executor, and what he does is he like takes all of these futures that we're running, and he like puts them where they need to go. So, or like, sorry, he puts them all on a list of things he's executing, and then when they are like sleeping, they're like get a little tired, they have nothing to do, take a nap. He like executes whichever ones do have something to do, right? So like our game loop, for example, for our like little brick baker game, he in his run loop, he basically sleeps for like 1 frame period every frame, right? And so what happens is the executor goes like, I'm gonna like run the game for a little bit. Oh, it's sleep time. I'll go check if there's anything to do on this guy or this guy or this guy. And so what would be nice is eventually for if we have 2 things to do literally right now, we could like execute half of it on one CPU and half on the other. So I guess we could start trying to think about what that would look like. Is that what I want to do right now? I guess no. I think what we should do right now is probably we've kind of like left some shitty code around. Like I don't want this like boot stuff to live in the ACPI parsing, and I want to like unit test the ACPI parsing and stuff. So I think probably what I'm going to do is just spend the next hour doing some cleanup, and I guess I'll keep streaming if people want to watch. They can, but I'm not going to be doing anything new feature wise for now. So we'll call this like kind of like the end of today's goals. We'll say dispatch function from bootstrapper processor to secondary processor. Oh, actually, I just remembered. We actually have to. The stack is fucking broken. We only support 2 CPUs right now. So let's do add support for greater than 2 CPUs. Damn, I checked your channel and your OS has so many features. Is great. Yeah, thanks. Appreciate it. We're trying out here. Okay, so let's quickly commit this and say checkpoint dispatch function from bootstrap to AP, application processor. And maybe what we do now is we fix the 4-core stuff. So if I were to look at my bootstrap or my trampoline code is what they call it. This is what runs when we start up the CPU. And the only things we really want to do here is we want to get from 16-bit to 32-bit mode. This code is all fine, right? This like there's nothing that is like CPU specific about this. We can do the exact same thing on everyone. But the second thing we do is we're supposed to initialize a stack for this CPU. And right now I've just hard-coded the same stack for every single one. And what we have to do is we need to, what would be nice is if we could like dynamically allocate a stack for each one. So what's happening here is, how do I draw this? We have like our executable, and he has like a defined memory layout that's like set by the compiler. So like here we're gonna have like code, and here we're gonna have like constants, and here we might have like static memory. And one of the things that we stick in there, where static memory is like BSS is the name for him. And so what we do is before we run any code, we say like, hey, when I make like local variables, I have to put them somewhere, right? Like when I'm in like main and I say like, let's make like a dummy function. Oh, I already have one. Like if I write like a function main and I say like, let x is equal 4. And then I say like, return x plus 5 or something. This is like kind of a bad example because this could all be done with registers and no memory accesses. But let's just pretend, for the sake of this argument, that like this, well, or we could do this. We'd say we have like lots of variables. B, C, D, E, F, G. So many variables that we can't fit them all in our registers on the CPU, right? There's like too many. Some of these guys are going to have to hit memory somewhere. And so what they do is there's like this guy, ESP, he's like a register in the CPU, and he keeps track of like, where in memory am I? And so like what he does is he says like, oh, you want to put x equals 4? I'm just going to like stick 4 on the stack. And I'm going to like say ESP is equal to like 0. Say he's like at address 100. He's going to be like, oh, I'm going to go to like address, he's going to go to address like 0x1004. I think he subtracts actually. So I think that goes like 0, F, F. Oh, what's like F minus 3, F, D, E, C? He's gonna like move back 4 bytes, and he's gonna say, okay, I'll put that 4 in like that memory here at like address 0xFFFC. And then when you like put the next one in, I'm gonna just pop it back. But he like needs somewhere in memory to put that thing. And so what our like stack initialization stuff does is we've put a section in static, what we call like stack. And this has worked fine up until because we only had one CPU. We just say like, here is our stack. But now we have like multiple CPUs. And how do we know if we have like 2 CPUs or 4 CPUs or 11 CPUs or like 100 CPUs? Do we want to pre-allocate stack in our like executable for those many? That's wasteful if we don't have exactly the number that we allocated for. And so what I kind of thought would be fun is like this gets loaded into memory at like 0x1000 or something. And then like over here, we just have like this whole big chunk of like unused shit. And so really like this stack for others, like maybe it should come from here. Maybe we should like pull out a chunk of memory over here and say like stack 2. And like then we like have like vectors and like frame like pictures and stuff. And like then over here we're like, oh, we're another CPU 3 can go here. That's kind of like what I thought would be nice. And so like the way I was thinking that you would do that is you might like allocate like a temporary, you might in here define like a temporary stack that you're allowed to work with only for the purposes of allocating another stack. And now I'm just thinking like, do I want to do that right now? Nah. I think this is too much overhead. This would be like too difficult to implement for what we're doing, right? I could instead just allocate for 8 CPUs, allocate 16K for 8 CPUs. That's like what? How much memory is that? 16384 times 8 divided by 1024. That's like 128K. So like, who gives a shit? Right? So that's what I'll do instead. I went through all that explanation to say, never mind, I don't want to. And instead what we'll do is we'll just say we have times 8. We'll just say we have 8 CPUs. We'll define our number of CPUs directly. So we'll say, I think you say what? We'll define a static variable that we can reference from our codes. We'll say set nums max num CPUs is 8. I think we put a comma here. Where's this like set? And this is like basically assembly's syntax for define, right? It's the same thing as saying like define maximum CPUs 8 in C. It's just like a name that you can use. Then we'll say set stack size is equal to 16384. Okay. And so here we will say stack size times max num CPUs is how much we want to set. And then we skip another... We had this problem where we were like colliding stacks before. Where like the end of our stack was like colliding with another variable. But that's okay. That's okay. I actually think it, well, we'll see. We'll see if that's actually a problem. I guess we can leave that skip point in there. Fuck it. Okay, so what will happen is CPU 0, when we boot, will take this stack. But I guess we don't actually know that this is going to be CPU 0. We're kind of assuming that this is CPU 0. So probably what we're going to want to do is we're going to pull out the CPU ID. And can I like make a macro for that? GNU assembly macros. Macro, my doesn't handle include and macro as everything starting with a dot is vector symbol or directive. Macro extensions perform along program assembly and cannot be done separately. What is it pitching? What is this question? Is there any way to have GNU only expand macro directives in a .s file, producing in a .s file without them? No? Okay, yeah, okay. That's fine. That's fine. So I can just say, what? We can like make a macro called like CPU ID, get CPU ID, and he's going to, I guess, just call CPU ID. So he's gonna just do this. And maybe we'll actually call him get CPU stack, or we'll say set CPU stack. And we'll just make a note that he clobbers EAX, EBX, ECX, and EDX, and ESP. Then we can say get the CPU ID, and then we have here EBX has the CPU ID. And what are we going to do? We're going to shift him left by the stack size, 2 to the power of the stack size. Sorry, how do I say this? I want my stack. So I said here that I want my stack size to be 16384 per CPU. So what I actually want to do is I want to multiply this by the stack size. I could do a shift, but I'm not going to be so pedantic that like I'm worried about the optimization of like a shift versus a multiply in this like one-time CPU unit. I don't give a fuck, right? So let's just look up the like multiply command, x86 instruction. So there's mul, and I just mul the thing into the register. So I can just say mul stack size EBX, and then I can just move the thing in EBX to the stack pointer probably. Oh, I need to subtract this from the stack top. So then I say sub stack top from EBX. I think. And then I move EBX into ESP, I think. So I think what I'm saying here is I'm like, set up my CPU ID call CPU ID, get the number from the CPU, like get what my CPU number, multiply that by the stack size, so it should be something between 0 and 8 times 16384, and then I offset into my stack by that number, and I put that into the stack pointer. I think that should be what I want. And so here, let's, I guess, just start here by saying set CPU stack. And sure, that seems reasonable. And then I guess in AP startup, we've kind of like fucked up what EBX is. So in main, or sorry, it's in multi-boot now, multi-processing. We just will change this from using the passed in CPU ID to here he'll just call multi-processing CPU ID manually. Get it himself. Okay. And I guess we'll just instead say let CPU ID is equal to CPU ID. There we go. Ooh, let's see if that still does something sane. So here he doesn't like that there's no end macro. That makes sense. We do have to end the macro. He doesn't like multiplication without a size suffix, so we'll just mul with an extra L. He doesn't like that either. Invalid operand for instruction. So let's look at the multiply instruction. Where do I find? Here we go. Unsigned multiply. So there is. Oh god, I have to remember what all of these mean again. So M32 I thought meant immediate. Performs an unsigned multiplication of the first operand, destination, and the second operand, source operand. This stores the result in the destination operand. Operand is implied. Operand located is AL, AX, or EAX. The destination operand is an implied operand located in the register. This guy, EAX. I see. So the result is stored in register AX. Wait, why the result is stored in register AX, but what about the destination? Oh, if I use the implied version, I guess, then it would use EAX. Can I see like an example of how to use this? x86 small example. What the fuck? Okay. Move 5 into AX, move 10 into CX, and then multiply CX. Oh. I guess they're saying that I do have to use EAX. Okay, that's fine. Fine by me. Fine by me. So here we move stack size into EAX. We move the CPU ID into EBX, which we already have. And then I guess we just say mul EBX. And then we should have this in EAX. Okay. Cool. I guess we should actually probably add the stack bottom here. I think. Okay, so now let's just see if we can like print out. This is running, right? But I just want to make sure that the stack that we got is like what we expect, right? So here we can go into GDB again. And I think GDB, our GDB script that like sets our breakpoints and stuff, I think is already in the right state to check this. So we'll say gdb-x run.gdb. And we'll just write info registers. What did we set our stack to? 0. That's fucked. That's not good. Let's check what's in here. Oh, because maybe we haven't set our stack yet. Where are we? No, we are not here yet. Here we're about to set our stack. We're actually like very close, right? Here is the code we just wrote, where we say move stack bottom into EAX, multiply or move the like stack size into EAX, multiply it, add the stack bottom. So here, now we should have our stack set up. So let's check info registers. Where did we set it to? 0x217000. Okay, and is that a sane address for where our stack is? How do I objdump -s maybe? How do I like print my objdump it's -x? Oh no, nm is what I want. mn -c target target debug kernel, and we look for stack top. And stack bottom should be right next to them. Solid. So you have stack bottom of 2, 1, 3, and stack top of 2, 3, 3. And which means that our stack of 2, 1, 7 for CPU ID 1 is a 4 increment from this. That seems reasonable to me. That's pretty close. Except our stack grows in the other direction. So I think we did actually want, instead of stack bottom plus, I think that what I wrote for CPU ID 0 will just like, it'll put it stack at the bottom and move it directly out of our stack range. So I think I need to add in, we need to add 1 to our CPU ID. So here we'll just say what, add 1 to EBX. And now I think that we'll be in a reasonable spot. I think so. Let's just double check. Source run.gb. We breakpoint at our multi-core boot up. Say next instruction. Oopsies. That's interesting. So I guess, did I fuck something up? Let's just double check that my breakpoints are set at the right spot. So AP startup or trampoline is where we're going from. We want to look at just before, after we set up our stack, but before we jump. So that's here, 104. So we want formatted as hex, 104, hex 104 minus hex 50 for the start of our function. It's B4. And we're going to set our breakpoint in GDB to B0x80 this. So this should breakpoint us right before we jump to that spot. So we say gdb-x run.gdb, and we should break just at that long jump. Solid. And we say info registers. And here our stack pointer is 21B0000 for CPU ID 1. And if we look at where our stack range is, stack top, that gives us, that's 8K away from 3, which is perfect. That's what we want. Sorry, not 8K, 0x8000, which should be 32K. Perfect. Perfect, which means that CPU ID 0 would get 4K in, or sorry, 16K in, and then we have up to 8K stack. Perfect, 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 perfect. So now we can just call this set CPU stack from this guy as well. Instead of using the instead of assuming that we're CPU ID 0 on the Bootstrap processor, we pick the stack for our CPU. And now we shouldn't collide if we had like 4 CPUs. Yeah, I think that's good enough. And I think if I go to main now, or if I go to my wrapper and I just set in 8, it would be interesting if we could like print out each of our stack pointers as we start. How do I want to tackle this? Is there a way? I don't really, whatever. I think we can probably just cargo run again. And in GDB, we can just check where each of our stacks goes. So source run.gdb. Oh, except my breakpoint's in the wrong spot again. I have to obj dump and calculate the offset again. Ugh. So where's my long jump in here? It's somewhere. 104. Oh, same offset. Sick. Sick, sick, sick. So let's just, yeah, source run.gdb. Oops, I have to gdb equals 1. Cargo run. And so hopefully now I should breakpoint there, but nothing's really happening, which is kind of interesting. Oh, it's because we panicked. Ooh, hit a little assertion somewhere. Ooh. Okay, so we fucked up our initial stack, I think. That's interesting. Can I, like, look at my stack pointer here? 216FF8. That seems reasonable. Was that within our range? Let's look at our symbols again. NM-C. Stack top. Yeah, so we do have 216, which is just under 32k above this. I wonder if we have our global descriptor table issue again. Let's think. Why would we be unhappy? So can I maybe like... Oh, did I just forget to push? Did I just fuck this up? Maybe... So before I was supposed to have... Oh no, yeah, here I should have pushed the stuff onto the stack that I wanted. So I guess let's just look at this stuff when we push the multi-boot headers. Did I make a mistake there? Oh, of course I did. Of course I did, because this set CPU stack stuff, it clobbers EAX and EBX. So I need to stash those somewhere. What registers do I have? Can I stash them somewhere else? CPU registers x86. EBCD. Oh, is that really... Do I really only have 4? Oh, that's fucked. So the problem is, multi-boot comes in and he says, hey, here's a bunch of info for you. I've stored them like handily for you in the EAX and EBX registers. Great. Works for me. But then he says, then I say, wait, but I need to like check my CPU ID. And in order to check my CPU ID, I have to use EAX and EBX. So then I clobber that info. And then I say, well, let me put that stuff on the stack, but it's already wrong. But I think what I can do, let's just get a little crazy here. We can just manually put this stuff where we want it. So I think that there's like, how do you put stuff in memory? Move from register to memory x86. Because even though we don't know which processor stack we want to use, we still know that no processors are using the stack right now. So we can just put it anywhere in that area. And that'll work for us. So move. Oh, can I just move to an address? x86 assembly move from register to memory. Moving between. So here, I want like here. Having flexible to encode OR DISI would have instruction longer. So what is... Okay, do I have to put the address in a register? Move to T cursor, T last. Move by T. Oh, okay, no, that's fine. Okay, so I can just say move EAX to stack top. And do I have to dereference it? I can't remember like the syntax for AT&T. Is it like this? I think this is how you do it. I guess we'll see. And then here we just move back. Well, let's see if this compiles. That does not compile. He doesn't like that. Maybe I just do this. Okay, and then here, can I just put him back? So here, I say move stack top into EAX and move stack top +4 back into EBX. Okay, and now if I go run release, do I still... assert on that problem. Oops, I need to cargo run with GDB. GDB equals 1. And then I source run.gdb. Backtrace. So we are still panicking, and the multi-boot stuff is still wrong. So maybe let's, fuck. I hate how hard it is for me to find what I'm looking for here. So maybe I move, what is it, stack top. Oh wait, do I not put it in brackets? Maybe? That sounds right. I think that raw numbers are memory accesses in this, but it still doesn't like it. So maybe I can like look at what's in EX and EBX here. Just like fucking bullshit. Let's what makes most sense here is probably to debug instruction by instruction, the assembly stuff. So if I obj jump here and look at start, I can just breakpoint here. This does look right to me. So can I set in my GDB scripts, I can just say breakpoint at this address, please. Thank you. And then I run my thing, my OS. I run my GDB script. And I can say print, let's like dump memory at maybe like 10 bytes or 2 words at stack top, which has an unknown type. So we can just cast this to a int32 star. No, int star. Okay. So stack top is 0x0. What the fuck? That's not right. Here we have this defined as, here we'll just try to do this. X, 2 words at stack top. Okay. So there, we've pushed something to the stack. And can I, are these printed as hex? Can I like, here we go. So is this the multi-boot magic? It should be. I guess we can double check info registers. EAX is its value. So we did push EAX and EBX to the right places in memory like we wanted. So now we can disassemble start. And let's just next instruction, next instruction, next instruction. Where the fuck are we? So we want to go all the way down to 1, 2, 3, 4. Oh, okay. What the fuck is going on here? Oh, this is right. So we want to go all the way down to this instruction here. So that's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So here, we should move this stuff that we stashed in memory back, right? So if I say info... So first, let's maybe look at... Ah, fuck. Is it because of these pushes? Why are these... Oh, I just pushed in the wrong spot. Fuck off. I'm... Wrong order. Wrong order. So I like put that stuff in memory and then was trying to pull it out and then put it back on my new stack. And then instead, I just put something else on my new stack and then pulled them out of memory, just like in the complete wrong order. God damn it, that's so annoying. So let's just source run.gdb. We're gonna breakpoint. We're gonna hit continue, and we should actually boot our OS now. No? Oh, yeah. We're doing stuff. Let's run without GDB. Maybe we're stopping too early. Let's just see what we get. Yeah, okay. Very nice. Very cool. This doesn't look very correct. 1, 2, 3, 4, 5, 6. We have 7 CPUs booting, but they haven't got their CPU IDs correctly. But I think that what we did is like fairly correct. Let's maybe look at the CPU ID stuff. Multi-processing. Where is this hello from CPU ID coming from? CPU ID booted. So maybe over here, we'll just say print EBX. What do we have in here? So interestingly, we do have duplicates here. That's not good. Which kind of makes me think that there's a bug in here, and it also makes me concerned about our stacks clobbering each other if the CPU IDs are the same. Can we just like move one EAX? This. Call CPU ID. Does that change anything? Oops, he doesn't like that. Why not? Unknown token expression move. One. What the fuck? Is it because I put a comma? Am I high? What am I doing wrong here? Move one into EAX. What the fuck is the problem? What the fuck? Unknown token expression move. Oh, is it because like I did this? No? I must be missing something. Oh, oops. Syntax. Oopsies. It's options HTT syntax. I missed this. Now it will let me do that. Yeah, okay, so that's the same thing where I get the same like duplicate responses from CPU ID, which is really weird. CPU ID, duplicate ID, QEMU? Because there's clearly something wrong there. Not sure. I'm pretty sure that we're calling this like CPU ID function, right? Right? It says like if I call it with EAX is equal to 1. Where have I seen this before? So input EAX equals 1 returns model family stepping information. So model family processor. Oh wait, this is wrong. What the fuck? Oh, returns additional information to EBX. Here's what we want. When CPU ID executes with EAX set to 1, additional information is returned to the EBX register. Brand index, low byte of EBX. This number provides an entry into the brand string table, blah, blah, blah. Don't care about that. Don't care about this either. Local APIC ID, high byte of EPX. This is numbers the 8-bit ID assigned to the local APIC on the processor during power up. So is it possible that the APIC IDs are wrong? Like QEMU CPU ID APIC ID. APIC. Yeah, I'm not seeing invalid local APIC ID. Extended topology. Description problem. After post copy migration. Okay, this is much more complicated than I want. I'm gonna do some Googling about this off stream, I think. I'm like pretty goddamn sure that this CPU ID function, I'm doing the right thing. I'm like very, very, very sure. But I mean, I've been wrong in the past, you know. And I think probably what I'm gonna do is I'm just gonna do some reading off stream and try to see if I can figure out where I've gone wrong. Otherwise, I'm pretty happy with what we've done today. We got like pretty quick into dispatching functions from the Bootstrap processor to the application processor. And we've like proven out to some extent. I shouldn't say proven. We've set up a stack manipulation thing so that each CPU should get its own stack up to 8 CPUs because we've allocated this. Somewhere we're still going to have to like pipe this information back into Rust so that it can avoid booting a CPU ID greater than 9. And so now where we're just struggling is like, why the fuck does this CPU ID command not give us the expected results back? But that's a problem for later, Mick. Thanks for watching. I appreciate you if you've enjoyed what you've seen. And if you've enjoyed what you're watching, I stream most days at around like 1 or 2 o'clock Pacific time for 1 to 2 hours. And if you miss a stream, you can always check out the YouTube and all the VODs will go up there. You can catch up, do whatever you want to do with that. YouTube is linked in the Twitch description. There's like a little YouTube logo at the bottom. And if you're watching on YouTube and you want to pop by, say hi, talk about what I'm working on, whatever, yeah, feel free. Twitch is linked in the YouTube description. And yeah, like I said, most days from 1 to 2 Pacific time. Yeah, thanks for watching. Catch you on the next one. Bye.